Hello everyone, my name is Wentao. Today I will introduce my work, Large Language Models are Learnable Planners for Long-Term Recommendation. This is a joint work of USTC and Meta AI. And my talk will about three parts: introduction, method, and experiments. Let's go to the first part. Okay, I will first explain why we need long-term recommendation. As introduced by previous work, we can say in traditional sequential recommendation setting, at each time step, our models aim to suggest the next item a user will be most interested in. However, this approach overemphasizes the immediate response. This will lead to maybe echo chamber effect, where users are repeatedly shown similar items, causing potential boredom. So, to solve this problem, it is essential for us to investigate long-term recommendation as shown in the right figure. We should consider the user's entire interaction sequence to maximize their long-term engagement. So this will give us a more diverse and engaging experience. To achieve that, it is crucial to integrate planning capability into the recommendation process. That is to say, we should develop a policy that takes into account not only immediate response, but also long-term consequence. So, however, acquisition planning capability is not non-trivial. Existing work primarily employs reinforcement learning, and they train a new model from scratch with the objective maximizing cumulative reward. However, these approaches are entirely data-driven, and the efficacy is significantly constrained by the quality and quantity of available data. As we all know, the recommendation data is typically sparse and naturally long-tail distributed. This will result in suboptimal performance, particularly for these sparse and long-tail items and users. So, recently, large language models have emerged with powerful planning capabilities through pre-training on massive textual data. As shown in the figure, a lot of work has shown that large language model can break down a complex works into several subtasks and execute them subsequently. By conceptualizing a multi-round recommendation as a complex task, we can also do it. We can harness the planning powerness of large language model to devise a multi-round recommendation policy, which aims at maximizing the long-term recommendation engagement. Yeah. However, direct acquisition such planning capability is non-trivial due to there are substantial domain gap between the LAM pre-training task and recommendation task. Concretely, the large language model may not understand the recommendation principles. It also don't know how to conduct personalized recommendation. To overcome these challenges, we propose a bi-level learnable planning framework that is macro-learning and micro-learning. They can acquiring high-level guiding principles and also planning personalization respectively. Okay, I will introduce we introduced the idea of exploring the planning ability of large language model with a bi-level planning schemes. Our framework is shown as below. There contains 4 modules: reflector, planner, actor, and critic. It also consists bi-level learning mechanisms like micro-learning and macro-learning. We first focus on the main step of our framework. It contains 2 main steps. First of all, we use the planner to generate problem-solving plans, or we can say the source. It breaks the recommendation task into sequential step-by-step subplans, and also striking a balance between exploration and exploitation. And secondly, we use the actor to custom the high-level plans into executable actions for each users. Such format is inspired by React format, which is a framework in large language model-based agent area. So, but purely based on such React format is not enough. As we said before, there are a substantial domain gap between LAM pre-training task and the recommendation task. To solve these problems, we propose BLEEP framework and employs hierarchical learning mechanisms. We first introduce micro-learning mechanisms. It involves the planner and the reflector to generate more appropriate plans, where the reflector extracts high-level guiding principles from historical episodes and incorporates them into the input of planner to enhance the quality of plans. Concretely, the reflector generates reflection based on historical trajectory and generates reflections and store them in the planner memory. And when the planner generates the thoughts, it will retrieve the most relevant reflections and enhance the quality of plan generation. In this page, I will give several examples of our thoughts to give an intuitive understanding of how our framework are working. We can find some interesting properties of our generated thoughts. In the first thought, we can say the large language model first analyzes the user's behavior and also analyzes user's interest. Then it will decompose the recommendation into several subplans. It will first recommend maybe action games and then recommend some niche general games. So it decomposes the recommendation task into several subplans. And for the in the example 2, we know that large language model can adhere to previous plan. It can maintain the consistency and the continuity of recommendation strategy. In this page, we will introduce the micro-learning. It involves the actor and critic module to generate more personalized recommendations, where the critic module can assess users' current satisfaction level. Formally, it is action advantage value. It was analogous to A2C algorithm. It can update the actor's memory to help to enhance a more personalized recommendation. Yeah. We can detail introduce the actor module. Every time it receiving its inputs like history, trajectories, and current state, it will incorporate three operations. Firstly, it will retrieving valuable experience from the memory. And secondly, it will utilize the tools to gather valuable statistical information of current state. And thirdly, it will integrate the results of the two-step and other input to prompt large language model to generate executable action to the environments. In this page, we will explain a very important and fundamental principle in our work. We assume that the policy updation in our work have a similar effect with traditional grading updates. That is to say, our approach based on in-context learning can learn planning without grading updates. As shown in this figure, we suppose the current state is ice, and we find a good action that is A2. The purpose of grading update is to adjust the policy that we can increase the possibility of sampling a good action A2 given the current state S. And we want to explain that our work that we can store the state action pair S and A2 into the actor's memory, and when encountering a similar state again, we can retrieve such pair into and prompt a large language model. In this way, we can increase the probability sampling action A2 also. So in this way, we can say the in-context learning achieves a similar effect to gradient updates. So it is underlying learning principle of our BLEEP framework. It is very important in our work. Finally, I will introduce our experiments. We conduct experiments on two datasets, Steam and Amazon. To better reflect the issue of filter bubbles, and we simulate the real-world recommendation scenario, and we introduce a quit mechanism. That is to say, the interaction will terminate if any of the following conditions are met. The first one is the similarity between the recommended item and the items in the recent recommendation list is below a predefined threshold. That is to say, you are repeatedly recommend similar items to user, and the user will feel boring. So it will quit the interaction. And the second one is the online reward is less than maybe a predefined threshold that we set to in there. That is to say, you are recommend items that the user doesn't like, so it will also terminate the interaction. So in this sense, we need a model that can effectively capture users' interest and mitigate the risk of continuous recommending similar items. We need such model. In this way, we can achieve a longer interaction trajectory and maximize long-term user engagement. We use 3 metrics to evaluate our model: trajectory length and cumulative reward and single run reward. In this work, we think that the trajectory length and the cumulative reward will represents a higher model performance, but a higher average reward or higher single run reward is not necessarily better, because excessively higher single run reward may indicate the model is overemphasis on immediate responses. Okay, we conduct experiments on 2 datasets and find that our belief framework consistently achieves the best performance over traditional RL-based methods and some large language model-based baselines across 2 datasets. It was mentioned that the React method, which also integrates the thinking process and the acting process, is performed worse than reflection and belief. This means that this underscores the significance of self-improvement in large language models. We need to propose learning mechanisms to bridge the domain gap between the pre-training task and the recommendation task. In addition to this overall performance, we also conduct in-depth analysis. We split the items into different groups based on their popularity. For the group 1, it contains items with highest popularity, and group 5 containing items with lowest popularity. We find that traditional RL-based methods A to C lack planning capabilities on these long-tail items, and our work can exhibit significantly better planning capabilities on these long-tail items. We also conduct application study to show that the absence of either of 2 learning mechanisms will result in a decline in performance. And if we don't use the micro-learning mechanism, we will find our performance will exhibit high variance. That is to say, the personalized recommendation experience is not applied to every user. It has high variance. We need to first learn the general recommendation principles. Yeah. In these pages, we conduct experiments to show that our critic model can estimate the user satisfaction level with lower variance. There are two methods. The first one is Monte Carlo estimation. It is an unbiased estimation, but it will have a higher variance. And the right one is our estimation. It effectively mitigates estimation variance, but presents a small bias. We also change the window size in the termination condition. We find that under different environments, our belief can outperform all baselines in all this environment. It's very robust. Finally, we conduct our experiments based on different base models. We find that there will be a positive correlation between the strength of large language model backbone and the performance of BLEEP. Okay, I will. In conclusion, in this work, we explore the integration of planning capabilities from large language model into recommendation. And to bridge the domain gap, we propose a bi-level learnable planning framework, improves the learning efficiency and adaptability. We also validate the capability of large language model to plan for long-term recommendation. This is all. Thanks for your attention.
Thank you. And,